All right, hello, hello. Let's get this thing rolling. I'm warmed up in terms of teaching, so.
You need a gavel or something.
Yeah. All right, so hello everyone. My name is Gage Hills. I'm a professor in electrical engineering here at Harvard. I work on designing integrated circuits or computer chips. So this panel is actually a follow-on panel to the one that my colleague Leshe was just giving down in room 206, which was sort of looking at the intersection of the power grid and AI, and sort of how this energy distribution is related to policy and incentivizing different power distribution companies to move power around. And a huge consumer of power these days, as we were hearing these gigawatt numbers down there, is data centers. And these data centers are computing a lot of these artificial intelligence workloads, training models. So you can sort of think about the context of this panel as being the energy and resources associated with, once the energy gets to the data center, like what's actually happening, like all the energy that's used for the sort of computing itself, but not just the computing. There's also energy and resources that's spent on, for example, the cooling or general infrastructure, or energy that's wasted in power conversion, which Yicheng is going to talk about. So this panel is going to look at how this, how we sort of, as I'd say we're mainly an engineering panel here, how we sort of look at these new challenges in computing from an environmentally aware point of view. So as just a quick summary, I'll give maybe like 2 more minutes giving this sort of high-level description of the panel, and then I'll introduce our esteemed panel here, all of whom I know pretty well. And then we have some, we'll sort of describe where we're working for maybe like 2 or 3 minutes, like relative to sustainable computing. And then we want to open it up for questions, have a nice lively discussion. We have some questions, in case, to get the discussion started, but we want to hear from you guys also. So like I said before, I'm a circuit designer. I've sort of spent my career so far in designing energy efficient circuits. So circuits that compute fast and use a small amount of energy. So I can sort of attest that, like, conventionally, at least my focus and the focus of the field has been on the sort of core computing devices themselves, like the integrated circuits for the computation, for the memory, the circuit boards, the architectures, the communication, stuff like this. But nowadays we're at this like really exciting time, and even like feeling it more in the last year or so, where this concept of a computing system is really becoming sort of more holistic. Right now, I would argue nowadays that even a full data center should be thought about as like a single computing system, because you have all these energy and resources that's used for, all the maintenance of the data center itself, right? All the cooling, the power conversion. So why shouldn't we be considering this in the overall optimization of the computing system itself? And I'd maybe even go like beyond that, and this is some of the stuff we'll talk about today, to say that the sort of boundary of the computing system shouldn't just be at the data center itself, but should even go beyond that, because we want to have some kind of interaction like with the power grid, for example. Like we heard in the last panel, Minlan talking about like very flexible data centers and being flexible to times when there might be more power available or less power available, but still meeting the overall application constraints of whatever it is we're trying to compute. I think this is a really exciting time, a lot of interdisciplinary challenges, and more interdisciplinary than I'm used to. I'm used to thinking of like interdisciplinary as like maybe talking to the material scientists and the software people. But now we got to talk to like the policy people and the energy people and even the environmentalists. This really, really fun time to figure out actually like what we should be optimizing, how we incentivize everybody to sort of work towards a common goal, and even like what is that goal? Like what should we be optimizing for? Should it be energy efficiency? Should it be like water usage? Should it be use of toxic chemicals, right? Like all these questions are going to come into play. So that's what we like to get you guys thinking about. We're thinking about it. So I'll start by introducing Ayşe Coşkun. She's a professor at Boston University. Go for it.
I think it's working now. Can you hear me? All right. Generally, I'm told that I'm pretty loud, so hopefully. So, so you might, So I'm Aisha. Thank you for inviting me to this panel. I'm a professor at Boston University. Also, most recently, I'm the chief scientist at a company called Emerald AI. It's a startup venture working on flexible data centers, flexible power in data centers, I should say. So I've been working a lot on energy efficient computing over the years, and that included a number of different things. As Gage was saying, going from, I'm a design automation and systems person broadly, so I haven't been making devices like Gage has been doing here, but basically how to design systems, system management methods, analysis methods, simulators, etc., to improve efficiency, looking into future technologies, how to put them all into a system, how does it work with the application, how do you manage smaller systems, larger systems, from going from mobile to all the way to data centers. So that's where I've been playing over the last decade and a half at BU. And also during the last decade, we have been thinking about data centers. Data centers have been big power consumers even before the latest, AI boom. And instead of looking into energy efficiency in a silo, we started thinking about data center as an ecosystem or as a citizen of the power grid. So then we started asking the question, sure, we should work on energy efficient computing, but how about thinking about data center in a way that data center can adjust its power consumption depending on the need? So for instance, if the grid needs data center to increase power because there's ample power and it's cheap, it can do that. If the power grid has a lot of other demand, like in a hot summer day, everybody turns on their AC, then the data center can reduce its power. So this idea really resonated with me. I started talking to power systems folks, and for over a decade, we've been looking into designing methods, optimization algorithms, simulation methods to how to make the data center do demand response, basically, or power flexibility in a more broader sense. And over the last year, that brought me to Emerald AI, where we are building the commercial scale data center infrastructure software to do this on real world data centers, essentially. So it's been a very interesting journey. So definitely, I think one last point would be to think more holistically has been something that has been evolving in my research and my work. So going from how to make this energy efficient to, okay, like what is the ecosystem? What do the users want? What does the grid want? Is there a concern about energy availability or carbon? And thinking all of these things holistically. So going beyond just energy, going beyond energy. And I also spent a lot of time on temperature, thermal awareness, and energy and thermal are kind of pretty connected to each other at different levels. But essentially that holistic thinking is pretty much what we need, I think, going forward. And that's it for now.
So next we have Yicheng. Yicheng's a postdoc at UC Berkeley, working in power electronics. He'll be joining the faculty at UT Austin at the beginning of next year. And he's has hands-on experience working on the actual power converter circuits at NVIDIA for some of the high-powered GPUs.
Yeah, thank you so much, Gage, for the kind invitation to this panel. And it's my great honor and pleasure to be here talking to you guys today. And so just now, Aisha shared her view on the design of the data centers, including how the data center loads can interact with the grid. For example, how the data centers can respond to the demand from the power grid. And so in that large picture, I saw my own research as a bridge which connects the power grid to the computer chips that we're using for AI, and also include those at the edge as well. And so my research focuses on the power conversion systems in data centers, and these systems converts the electricity from the high voltage that we use for power, the power distribution in the data centers, to the very low voltages that is required by the chips. Okay, and so typically it's from the 800 volt DC to below 1 volt that is required by the processor chips. And so now this voltage conversion seems very simple, but it actually brings a lot of challenges. For example, we want these power conversion systems to be small so that we can place them as close to the processor chips as possible. Also, we want them to be energy efficient so we can save the energy. Now, today we may not have the time to go through all of these challenges in today's panel, but I do want to focus on one particular challenge that is brought by the AI data centers, and this actually comes from the nature how AI consumes energy. And so if you look at the power profile of the data center chips, right, and it actually not constant over time. And so what you will see is it's constantly changing very largely. Okay, so when the GPUs, they are in the idle mode, they only consume maybe 10% of the maximum power. When it is running the tasks, it can consume 90% of the peak's power, and this change can happen in the microseconds scale. So this is very challenging. It can cause a very large power swings. And in the traditional data centers, this is not a very big issue because the server workloads tends to work in different times. So for example, the power drop in one server rack can balance the power surge in another one. So on average, the power that we see on the power grid is smoothed out. But the AI workloads, they actually tends to work in the same way. And so this means that the GPUs in the same cluster, they tends to require high power or low power at the same time. And these can cause a very large power fluctuation seen on the grid. And there's a recent study done by the Berkeley National Lab that shows, in fact, at the node level, this power fluctuation can be 50% or even higher, okay? And this can definitely not tolerated by the grid because it can cause the fluctuation on the grid voltage and also the frequency, which can threaten the stability of the grid. And to address this challenge, NVIDIA actually included a hardware fix in their latest data center rack design, which they add a very large bank of capacitors in their system. Well, it can definitely smooth out the power fluctuations, but the cost is also very high because the additional capacitors that you need to add to the system actually occupies 1/2 of the volume of the power supply unit. And as a power engineer, I believe we can definitely do much better than that. So we can do the same power smoothing and potentially much better power smoothing with a smaller volume. So this is kind of the question that I want to bring to today's panel, which is how can we stabilize the power of AI data centers? And I'm looking forward to hearing the thoughts from all the audience and also the panelists from the grid side, the chip level, and also from the edge. Thank you.
All right, before I introduce Vijay, saving the best for last. So I'll give just a little bit more details on some of the stuff that I specifically work on. We're sort of sitting in order here, maybe kind of down the stack and then outside the data center. But another thing that I find like super interesting, hopefully you guys will find it interesting too, is so far we've kind of been talking about the operational side of data centers and computing. Thinking about like how much energy is consumed, like while you're actually computing stuff. And that's all I ever cared about or even heard about before I came to Harvard. But there's also what I learned recently is this huge embodied side. And this sort of comes with the idea of like how much energy or how much resources does it take to actually physically build our computing systems. And in my case, like all the energy that's required to physically make the integrated circuits that are used for computing. And what we've found, and this is supported by other sources as well, that for many cases, the embodied carbon footprint or embodied energy consumption of creating a computer chip can exceed the energy that it consumes throughout its entire lifetime, even over many years. Of course, this is like application dependent. If it's a chip that's like inside a data center that's just like cranking away like all day, its operational energy might outweigh its embodied energy. But there's also applications, for example, some kind of like edge devices or some of the devices that Vijay is going to talk about, where when it's operating in the field, it doesn't actually use that much energy. It's a very low power device. And so this energy consumption of the actual physical manufacturing ends up being like the vast majority of its overall energy consumption. So the question that's sort of arises there is, well, should we be considering that energy consumption as part of the overall optimization process, right? Should we be considering these resources that are actually used to create the chip when we're sort of optimizing our computing systems? In a similar sense of like, okay, well, we used to just consider the energy consumed by the chip. Now we're considering all the energy outside the chip, consumed by the data center, right? Like this sort of goes to this more holistic analysis, but brings up some very interesting questions, right? Like if that chip is manufactured in the U.S., would you consider it differently than if it's manufactured in Taiwan and you're bringing it into the U.S.? Like, who should own that cost of energy consumption? Should it be the fabrication facility? Should it be the designer? Should it be the person that's using it in the end? So I think these are all sort of very interesting questions I'm working on that I don't know the answers to. But yeah, I also want to hand it over to Vijay. So Vijay is also a professor in electrical engineering at Harvard. Just got tenure a few weeks ago. So go Vijay. He's been working on a whole bunch of different stuff, computer architectures, tiny machine learning systems. I'll let you take it from here.
Congrats on joining UT Austin. So before I came here, I had tenure at UT Austin. And then I was like, well, why make it so easy on myself? The truth is my wife wanted to move here, and the only position they had was a tenure track position. So I was like, this is a tough one. Yeah, so I did tenure for my wife. That's all I like to say, and I just leave it there. Yep. Anyway.
Things you don't normally do multiple times.
Yes, exactly.
Going on the tenure
My
track.
wife honestly was like, I know you're crazy. She was like, don't get any crazy ideas about doing it the third time, because she was like, I know you. And I was like, no. But congrats on that. It's a wonderful place. UT
Thanks so
Austin.
much.
So folks, I work on everything that's outside of the data center. Yeah.
That's why he's lost.
Yeah, so I work on the edge. So pretty much if you think about your smartphones, or you think about your little, smart watches and so forth, how do you sort of bring in, technology into that aspect is kind of like really my sort of focus. And I think I'm really glad Gage cleared up one of the key points, which is like, I was looking at the title and it says sustainable computing, energy efficient systems for a climate conscious future, right? So I'm really glad that you clarified this difference about when we think about energy, typically it's not just operational aspect, it's the whole embodied aspect. I think for folks who are not necessarily well versed in the computing space, I think the best example that I heard from somebody was saying that at one point I was thinking, should I get an EV? Should I go get a Tesla because it's electrical and it's better and whatnot, right? And I already have like a regular car. And one of my colleagues was, works in the vehicle industry, kind of said well, yeah, it sounds great, but I'd honestly say you should just run your car down, because if you get the car, there's a certain amount of focus that you put on, it's a green car, but you're not thinking about all the energy that's actually gone into making that thing. So if you kind of look at the numbers, it's better for you to just use your old car, which was kind of a start kind of point. And I think that kind of like really helped me connect to this point about how should we be thinking about computing at large. And so from that particular context, when I think about your smartwatches and so forth, right, never get any attention. Nobody really sweats it, right? I mean, how much do you think about Alexa as being a big energy problem? Well, here's the way I kind of think about it. How many of us use plastic bags? We all use plastic bags all the time. A single plastic bag, you never sweat it, right? But then we all know where we are right now with plastic, right? We haven't planned for it, so what do we have? We basically have a whole bunch of trash. And so the kind of problem that I'm really curious and interested in is really thinking about the internet of trash, right? We're gonna have billions of these small little widgets all over the place. It's without doubt, because they produce too much value for us. We will build them, right? Regardless of what the effects are and so forth, knowing us as humans, we will continue to build them, right? But then we're not really thinking about the full life cycle, which is kind of like the whole theme, honestly, about sustainable computing, is really thinking about that whole life cycle. And so that's where I kind of come in, and that's going to be my whole kind of point, is like whether we should be thinking about data centers only, which is what everybody talks about, because I honestly think it's a lot easier to point to a big building and then put benchmarks and requirements and how people be responsible for things. But how many of us are really going to worry about how many of us have smartwatches in this room? Yeah, practically everybody's had a smartwatch, right? That's what's going to end up happening. but we never sweat the, what are the implications of building these small little widgets. I think that's the kind of, counterpoint that I'm going to bring to kind of help us understand what it really means to think about computing. And especially nowadays, I don't think we should be thinking about computing as like, oh, here's a computer. Because computers are fundamentally very deeply integrated into our fabric, right? So if you kind of look at like these small little widgets, you're going to have a lot of machine learning sensors in the future that are deeply embedded into, trying to build really smart buildings and so forth. And so there's a really interesting question there about sustainable computing from that standpoint. It's like, well, how much computing should this, let's say this new building have in order to offset, all the effort that's gone into actually, the embodied aspect that Gage was talking about. So I'll try to give you a very different perspective from that sort of viewpoint.
All right. Exciting. Okay, so I'm gonna just ask a couple questions. I want to ask a question to you two, then I want to ask a question to Vijay, and then we can open it up. So the question for both of you is, we've sort of talked about this flexible response and stuff like that, and we also heard this really interesting panel from Blair, who's right over there, on this interaction between sort of AI and policy. So the question is, do you think that from the sort of data center or computing point of view, you have all the signals that you need from outside? Does a data center have all the sort of indicators of, that power is available or not? Or do you think there has to be more sort of regulation there that needs to be stood up in order to make these systems truly sort of closed loop?
So the answer is yes and no. So if we, I like defining things. If we think about flexibility as being able to change power depending on, could be grid status. Like I was saying, the program could be merely just grid telling you that there's high demand and can you reduce your power for the next 3 hours. Could be more continuous demand response. Could be something else like some sort of a carbon meter. Right, could be green energy availability at the same site as the data center and the like. So basically, the problem of flexibility is adapting power to the need of that data center. And does the data center have what it needs in terms of the external signals? The answer is yes and no. Let's look into the grid side, grid awareness, because that's a hot topic right now with AI data center demand. There's a lot of demand. There's a huge queue of tens of gigawatts of data centers across the US waiting to be connected. And it's not trivial to suddenly expand the power generation and transmission to adopt all these data centers into the grid. So there's a long wait time. So there's a push. So there's a need for flexibility. And we look at the power markets in a lot of states, in a lot of independent service operator zones, there are demand response programs. So when you think about it, yes, there are mechanisms, right? If you think about, I was just in Europe last week, if you want to do carbon-aware computing, can I measure the carbon of this area? Sure. That, Electricity Maps is one of these many companies at this point that can tell you something about electricity, how green it is, can tell you something about price. So this stuff exists, but how does it connect back to the data center? Is there a standardized protocol? I want to build a data center. Sure, I'll make it flexible, especially if you put me to the front of the priority connection queue. Where do I connect? I don't know. Depends on the state, depends on the specific utility. A lot of these things are being developed as we speak. There are bespoke agreements. For instance, Google announced 2 new data center agreements with flexibility last month. They are not part of any standard program, essentially. So that's what I mean by bespoke agreements. But there is regulation coming up in a bunch of different states, a bunch of different, again, zones. So this is coming up. We are at Emerald AI, one of the things we are building. So one part is building the data center infrastructure, like orchestration software, so that you can do flexibility with performance guarantees to user workloads. And another thing we are building is this interface layer, essentially, because data centers and power grid folks haven't been in a lot of communication over the years, So it was, the way we design things have been, okay, I want 200 megawatts, and, I get power for 200 megawatts, and that's it, And then, I pay my bill or whatever. So we are talking about a different future now, where data center and the power grid has to interact. somehow the grid should tell me when they need to reduce power. And this needs to happen in a controlled way, of course. No data center will accept to operate in a completely arbitrarily regulated way. So there should be some control on, how many events we are talking about, what kind of program, what's the ramp rate, like what are the requirements of this, right? And similarly, the grid side needs to know more about the data center to be able to plan this. Okay, I'll give you 200 megawatts if you are flexible, and then, I'll have to know like when you are going to drop your power and this kind of thing. So we need to enable this communication. Is the data there? Sure. Is it flowing in both directions? No, not really, right? So when we talk to some of the utilities, like they want, like, sure, like we want you to implement flexibility, demo it, and then, like, what is the interface we should look at? It's a very fragmented space across even the US, and when you think about globally, it's definitely more fragmented. It goes everywhere between the grid calling, like phone call, the data center, to certain APIs, etc. So there's a lot of variety there in terms of how the information is coming. So we need better standardization, better protocols, more metrics, essentially. Also, lots to develop over there.
Yeah. I remember you saying when we talked before, it's not like there's going to be some telephone call like, "Hey, power's available, we'll start computing," right? Some kind of like.
But it's literally, when you first go and somebody's excited in this technology, like we want to demo, what should we do? And what would you do right now? Like if you had to, like, and this happened. Like this is not science fiction. Like California had a big power emergency a couple of years ago, and they asked the reserves to, kick in. They asked certain customers to reduce power. What do? Phone call. So unless you are part of an established program, which exists, then you are more regulated, like you get signals through an API perhaps, through some sort of an interface basically for people who may not be familiar with API. But generally speaking, yeah, it goes anywhere between a phone call to some sort of a computerized interface. So we need more. And maybe one final note would be, from the computer engineering standpoint, if you talk to people in software, hardware, measuring power shouldn't be a big deal. But if you think about the scale of things, it is still a big deal. So all data centers have a lot of telemetry in terms of, is this access available to the users, etc. There's a lot of gray area over there. So it goes both ways. So data center may not have everything it needs, so we need to build some new interfaces. But also, even for data center to have, like, advanced detailed measurement of its own stuff, there we could use probably better technology over there too.
Can I ask you a question that builds on that? So I certainly agree that yes, AI is driving a lot of power consumption. But I feel like back in 2010, when cloud computing was exploding and Google and all these companies were coming to life, then people were also talking about things and saying like, oh my gosh, computing on the planet is taking up like almost like a whole country. So can you help me understand, like, yes, the number's probably bigger, but I'm trying to understand, what, are we basically talking about the same thing? Like, I'm just trying to understand how to think about the problem.
Excellent question, and I'll explain with an anecdote. So I mentioned my story briefly, like I was thinking about data center energy efficiency and data center power grid interface for over a decade. So a couple of years ago, a former student of mine and I were like, we have a prototype working, so maybe this is time to think commercialization. So let's do customer discovery. Let's talk to data centers. And one thing we were thinking about is that data centers are big consumers, so their electricity costs us a lot. And there are interesting anecdotes. So that was our pitch. Like if you do power flexibility or demand response, you can reduce your electricity cost by half. And I thought like that there would be a wow response. They were like, we don't really need to reduce electricity costs, right? So, and we've been presenting these data centers consume 3% of the world electricity. Again, I was expecting this wow thing. People are like, 3% doesn't seem like a big number. Now, what's different today is essentially, like you said, the amount of demand. So we've been having a few percent increase in the demand every year. Now we are talking about integrating tens of gigawatts in the next 5 years, just in Texas. I guess I pointed to Vijay, but I should point it. So, and a gigawatt is roughly equivalent to a nuclear power plant's generation capacity. So we can't just put this energy into the grid like in a week or in a year even, right? So that's the problem. And when we don't do that, then the AI development is not going to happen as fast. Or some folks are advocating, let's just build gas plants everywhere and stop the decarbonization agenda and not retire coal plants, etc. Right? So this energy is going to come from somewhere eventually. So I think the power flexibility potential is that we have a lot of power normally. The peak times are the problem. So if we change how we design things with flexible computing, that's what we mean. Like 60%, grid is utilized on average 60%, right? So there's power there. So you can, if I wanted to put a megawatt data center, I can put it. When I want to put 200 megawatt data center, that's much harder. And if I say, I want 200 megawatts, but I'll reduce to 150 or whatever when needed, then maybe the grid can integrate me today, right? So, and without necessarily doing this massive infrastructure build out. So that's the difference essentially. Like data centers are waiting in the queue, the demand is huge. And if you don't find alternate solutions, then what's likely going to happen is that there's going to be a lot of fossil fuel-based power generation continuing to support our data.
So if I understand you right, then basically the problem was there previously when, we were building data centers back in 2010 and so forth, let's say, right? But then I'm assuming there was, infrastructure planning and so forth also being done there. And perhaps it's the fact that we have this new technology that has come into play, which is all this AI stuff, which works completely differently. Where we have such a thirst for it that we're going to scale it like crazy because it's applicable everywhere. So then that kind of really drives up the power, but then we're still on that infrastructure, whatever slow curve. Okay, gotcha. Thank you.
So I want to ask Yicheng a question because there's all this power flexibility sounds great, right? Like, having some flexible thing that can manage these huge swings in, gigawatt scale power swings. Like, how challenging is that to actually manage from the power electronics side? Like, usually when you talk about flexibility, you often are giving up something, right? Like, you're maybe giving up some efficiency. Is this like a practical thing to do from the power converter side? Like, can we manage these huge power swings on that side?
Yeah, thank you for the question. And in fact, this is what I've been thinking recently, what I want to do research in the future. And you are talking about how challenging it is to implement this kind of hardware in the data centers. So in fact, we already have similar power conversion systems for the 120 hertz systems, which we use on the grid right now. And we can apply the similar concept, which we call the energy buffer in the system that can help us to smooth out the power fluctuation from one side to the other side. And now, if we want to apply this concept for our data center digital loads, then definitely we need to operate this system at higher frequency. So we need faster switches that can help us to act at a faster speed. So that is definitely something we need to add in the data center hardware. And also, in addition to that, we were just talking just now, so the power swing in the data center can happen on very short time scale. And so that means if we want to add, for example, some capacitors or other forms of energy storage system into the data center, then the energy storage components needs to handle that spike current or that high power in very short time scale. So in that case, we will need some improvement in the material science and in the energy storage solution. So that's what I've been thinking about, and I've been looking forward to hear the thoughts from other panelists as well.
Maybe since we just have a few more minutes, see if, question here?
Yeah, I'm very curious about what the panel thinks are innovations you see on the horizon that could fundamentally lower, like by a factor of 10 or 100, the energy used per compute. You've talked about the embodied carbon and the embodied cost and the power supplies and the flexible demand, but fundamentally, it's the energy used per compute. What do you see as the potential to reduce that by a factor of 10 in the next few years?
Go ahead.
Well, yeah, so one thing I'll say is that this is basically the question we've been trying to answer for many decades, just from the energy efficiency point of view. So actually a huge contributor to the energy in computation, when we think about computing, I actually think about a much bigger system than just the computing chip. Actually, once the data is actually inside the computing chip, the computation is very energy efficient. But actually, most of the energy is wasted in the data communication, both from like going from like the computer chip, even to like a memory chip on the other side of the circuit board. And nowadays, like in these data centers, when you hear about these, hundreds of thousands of GPUs that are all like in a warehouse, now this communication is going from like one side of the data center to the other side of the data center. And some of the stuff that we're working on, so then that communication is a huge bottleneck in terms of the energy consumption. Because often what people are doing now is having these optical communication links, because light goes very fast from one side of the data center to the other side. Not instantaneously, still takes many computing cycles. But the energy that's wasted in an optical communication link, you hear some of these numbers like maybe it takes around 1 picojoule of energy to transfer a bit from across an optical link. But if you think about how much energy is actually stored like inside a memory, if I have like a bit, like a circuit that's storing a bit in memory, that typically takes like less than a femtojoule of energy that's actually stored there. So we're literally using a picojoule, like 10 to the minus 12, to transfer a femtojoule of energy, which is 10 to the minus 15. So, and that's like state-of-the-art technology, like 99.9% inefficient is like the best that we have there. So my group, I also didn't know anything about these optical communication links. That's some of the stuff that we're working on now, is basically how can we improve these optical communication links. But that's just at one level of the computing stack. That's sort of material science, circuitsy. But then there's also the sort of architecture stuff that.
So I was going to say something complementary. Actually, this is an excellent answer. Like much better than I would have given a version of it probably about communication. But it's important to think about efficiency and demand not being the same thing. Computing did get really more efficient over the last few decades in terms of the hardware, in terms of the software, and it will get more efficient. Hardware will get better, software will get better. Google, for their AI models, just looked into 1 year, just 1 year, of their AI models' carbon awareness, and showed in a recent paper 30x reduction in compute per carbon. So now, Vijay also comes from design automation background like me. If you are doing 30x improvement in something in a year, that means you were really inefficient to start with. And that tells me probably we are not at the saturation point yet, right? So we'll see a lot more improvement. But is that going to reduce the overall demand? That's really questionable, because generally what we do is to find more interesting things to compute, right? And this has been the case. Like, now it's more efficient, so let's do more of it. Or, I want to do this kind of AI on my phone. And, we come up with, there's this quote that I like a lot from my advisor's advisor, Giovanni De Micheli. He said once that computing is like potato chips, like there's never enough. You always run out, So I mean, it's good to think about that. While we are pursuing more efficient computation, we shouldn't just assume that the problem is going to be resolved by efficiency, right? So,
I think to add a couple of specifics. So you're asking about the efficiency element, right? Like as Gage was pointing out, the difference of moving data or bare within the same chip, kind of within the same system, kind of thing. It's about 1,000x right there. Right, so it's obviously we worry about the compute, but actually compute's damn efficient right now. So I think it's the data movement that's actually really killing us, and that's why he's talking about optical connectivity.
Yeah, question.
So I know we have a lot of electrical engineers up there, but I would just ask you, like, when you think about these problems of the power consumption, and it's not only your group, but in other groups they were talking about, the data centers may have to power down, which seems to me to be a very expensive thing, because of the peaks, things like that. But how do you apply financial tools? I'm an electrical engineer, by the way, but I'm wondering if you apply financial tools, like thinking about the cost of capital and the relative elements of the system in terms of how to, in terms of, well, do you prioritize more power plants in the short term, or do you power down, the NVIDIA chips, which is an extremely expensive product to be powering down? And to what degree do you embed financial tools in these decisions? Because ultimately, that's how a business has to evaluate trade-offs.
That's a question for me, I think.
I think everyone.
So I mean, I'll tell from, for instance, because there's a company, Emerald AI, and at the end, the company has to have some money, revenue, and need to sell that product, right? So there needs to be business value. It's an excellent question. GPUs are very expensive, so right now that's one of the limitations when you tell people like I'm going to curtail your power. They're like, well, I just spent this, $100 million to build up this cluster. Are you kidding me? But but the thing is, I think that in terms of the finance, there's a strong part, and our big value proposition, essentially, by doing flexibility to the AI side, to the tech side of this equation, is faster connection. Would you rather wait 7 years? And these are real numbers. Like Dominion in the PJM territory is giving 7-year wait times to data centers. Like, do you want to wait 7 years for your data center to connect, which is eternity in the world of AI? Or do you want some curtailments, like 100 hours a year, let's say, something that we can put constraints on, and then you can connect in a year. And then you'll be curtailed a little bit in a controlled way, and we'll only curtail the workloads that are flexible, so nobody's going to feel anything. So everybody will still be happy at the end of this. So this is the big business value proposition. There's another financial part in compute flexibility. Like I mentioned, demand response, generally, you don't have to be a data center. If you do demand response, the utility pays you something back. This never motivated really the data center businesses so far, at least the big companies. Maybe small data centers are different. But in the future, that might be different. We all read and sometimes feel about the electricity prices increasing. That's a global trend. Electricity is getting more expensive. So eventually, doing something that's good for the grid to get some money back, I think will be part of the financial equation.
I don't know how many have heard this. We all use ChatGPT, right? You'd be surprised when OpenAI folks actually came out and said they calculated how much power and money savings they'd be able to get if they just got ChatGPT to stop saying please and thank you. You can look it up. It's real. If they just got the model to not be so nice all the time, they were like, well, that'll save us millions of dollars and a huge amount of power. Because it's every token, right?
Do you have a question, Le?
I have a question on the power electronics side. As you know, the field of power electronics have spent the past 20 years trying to figure out ways to integrate renewables on the supply side. A lot of design innovation, a lot of great professors like Professor Pilawa coming out of that era. Now you are entering this new era where a lot of your focus is focusing on designing the power electronics for the demand growth, such as AI computing centers. What are some of the innovations you see that are different from the previous design for wind and solar inverters?
Yeah, that's a great question. And in fact, from my own research and works, I think one innovation that we did is which we innovate new circuit topologies that can utilize high density components in our circuit. So for example, we did a survey that in our circuit, we typically need either inductors or capacitors to store energy in our circuits. But we did a survey and find that capacitors can have 1,000 times more energy density compared to inductors. And so that means that if we can utilize more capacitors than inductors in our circuits for power conversion, then we will be able to greatly reduce the size of our power conversion systems without decreasing other performance. And so utilizing this concept, we were able to greatly shrink the size of our power converters. And in fact, this is very important for AI power delivery because maybe you cannot imagine that in the data centers, a GPU, it will need a current that is beyond 1,000 amps. Okay, so that is the current that you can use for soldering and welding. So that's a very high current. And as you can imagine, so for every inch between our power supply and GPU chips, okay, where this high current flows, on every inch we lose energy because of the resistance on the conduction path. And so if we can make our power converter smaller and smaller, then we will be able to place the power supply modules to be closer to the chips so that we can reduce this cost and help us to save energy. So this is one innovation that we did. And we also do innovation in terms of control. And here, I guess the challenge is the speed of control, because for the renewable energy, usually that is connected to the grid. So we operate at a frequency that is more closer to the grid frequency, which is the 60 hertz. But for the data center digital loads, okay, I was talking about the current beyond 1,000 amps. And this current can change in hundreds of nanoseconds. Then how can you build a controller in order to follow up with the change in the load current? And I was just talking about the load current can change from 10% to 90%, meaning that you need to supply, for example, 1,000 amps in just 200 nanoseconds. And so that means we need to use faster switching device, faster control techniques, better sensing technology, something like that. So this has become an intersection of power, circuits, packaging, control, and more. Yeah, so just to give a few instances for your question. Yeah, thanks.
All right, well, we are out of time, but we'll all be here. Just the panel, not computing. But yeah, we're around. I think Aisha has to go, but I think the three of us will stick around for a bit. But yeah, thanks so much, and thanks to the panel again.